going to take a look at what's called the Argand diagram. This is how we represent complex numbers geometrically. It's actually something very familiar to us. It looks very much like the number plane, which is nice and convenient. Our x-axis now is technically the real axis. It's the number line, the real number line. And down the middle we throw in an imaginary axis. What this means is we can plot any point. Sure, the real numbers like a equals 2, that'll still be on the number line as normal. Now we have a way of plotting this pure imaginary number of negative 3i. I plot it on the imaginary axis. And then ones that are a mixture of both, well, it's just like plotting coordinates. Minus 2 plus I, there I plotted at minus 2, 1. 4 minus I, over there at 4, negative 1. 4 plus I, 4 plus 1. Now that brings up the first interesting thing about looking at it geometrically, because we can see things straight away. And what we should always see is conjugates are always going to be reflections in that real axis, because it's just the imaginary parts changing sign, plus or minus, the real parts staying the same. This one here, the negative of 4 minus I, if we were to plot that, it's over here at F. What do we notice? Those opposite ones, where one's the negative of the other, basically it's a reflection through the origin, a rotational of 180 degrees there. And another important one we tend to look at is when we multiply by I. So if I was to multiply it by I, I'd get 1 plus 4i. And if I plot that one in, there it is up there. But geometrically what's happened? Well, when we multiply by I, we rotate 90 degrees. In fact, every time you multiply by I, you rotate 90 degrees. And that's why F is over here, because we've multiplied by negative 1, which was I squared. So we multiplied by I, then we multiplied by I. So we rotated 90 degrees, then another 90 degrees, 180 degrees. But the nice thing then is every complex number has a unique position. It's the only point that can be placed there. So we can identify every single possible complex number. So this then brings in this idea of locus, which we have seen in coordinate geometry, but now we're going to look at it on the Argand diagram. So let's start with the basics, the horizontal and vertical lines. If I was to see a horizontal line, well, what do I notice about every complex number? It doesn't matter what I plot on that line, they would all have the same imaginary value. So yes, in coordinate geometry we'd say, well, that's y equals c. When I'm talking about complex numbers, I can say, well, actually, that's the imaginary part of z is equal to c. Every one of those numbers would have that. And a similar thing would happen with the vertical. Instead of x equals k, we could now say, oh, well, that's the real part of z is equal to k. Circles are the other type of interesting shape we like to look at. And there's our basic circle, which we know would be x squared plus y squared equals the radius squared, if we were talking about coordinate geometry. Well, what we've seen is that x squared plus y squared, well, that's z times its conjugate. So we could write that as z times z conjugate is the radius squared. And every single point on that circle would satisfy that. So what would this particular one look like? Z plus 4 plus I times the conjugate of z plus 4 minus I is equal to 49. Now if I don't recognise it straight away, I'll expand it out and hopefully I'll get something that I'm familiar with. Now, still not 100% sure. So if I'm still not 100% sure, I'll bring it back to coordinate geometry. So instead of z and z conjugate, I can end up putting in the x and the y's. And I know how to deal with that in coordinate geometry. I'd have x squared plus y squared. Well, let's complete the square. And we end up with what we recognise to be a circle. So we know this is also a circle. Its centre would be at minus 4 minus 1. And the radius would be 7. So how could I have recognised that from the original equation without having to do all that working out? Well, this pattern will always be true. If I've got a factorisation where it's z minus some complex number, but then I multiply by the conjugates, the difference of those, so z conjugate minus omega conjugate, I see that pattern. I know, yes, that's a circle, and the centre is what I'm subtracting. So the omega radius is still r. Again, I look at this straight away and I don't recognise what it is immediately, so I'll play around with it. Let's multiply out by z conjugate. Yeah, still not 100% sure, so let's bring it back to what I do recognise. I'll make an x and y's. I've got 2x equals x squared plus y squared. It looks like we've got a circle yet again. Let's put in a form that I can play with. There it is. X minus 1 squared plus y squared is equal to 1. I know I've got a circle, centre 1, radius 1. Sort of. That's not 100% correct. Because you see, I turned it into x and y so I could solve the problem. And sure, here's the picture, I would think. But you always go back to what the original thing was being asked. And you go, hang on a sec. Originally I had 1 on z plus 1 on the conjugate of z. And I know I can't have 0 on the bottom of a fraction. So yes, it is that circle, but it would exclude the point 0, 0. That's not a possibility for this particular thing. Sure, it's a possibility for x minus 1 squared plus y squared equals 1, but that's what I changed it into to go and solve the problem. So I go back to the original one and just check and make sure, oh geez, should I be excluding a point here or is this okay? And in this case it wasn't okay. I had to exclude 0, 0. So 1C, starting with this idea of looking at things on the Argand diagram.